Now that we have an idea about how three-dimensional coordinates work, we can get back to talking about vectors. If we're talking about a vector in 3 dimensions, then our vector notation in component form is now going to have an x, a y, and a z component. In addition, we have the standard unit vectors I and j. They're now 3 components. Notice that there is a 0 in the z portion of those 2 vectors. And then we have a third unit vector, k hat. This is the unit vector that points along the positive z-axis. So we have our I hat, our j hat, and our k hat. Each one of these vectors is exactly 1 unit long, and when they're in the standard position, then they're located right along one of the 3 coordinate axes. These 3 unit vectors can make up any vector in 3 dimensions. And just like in 2D, we call this a linear combination of the standard unit vectors. So let's take a look at this vector v. The components of v are 2, 1, 3. I have it graphed here in this turquoise color, and I want to show you how the standard unit vectors come together to make this turquoise vector v. We have a 2 in the x component, which means we're going to have 2 of the I hat vectors. We have a 1 in the y component, which means we're going to have 1 of the j hat vectors. And then we have 3 in the z component, so we'll need 3 k hat vectors to take us to the to the tip of this vector. And so that's why we're able to write this as 2 I hat plus 1 j hat plus 3 k hat. So any vector can be written as a linear combination of the standard unit vectors if we please. Now keep in mind that I'm using pluses between my unit vector symbols here, but if you did have a negative, that would just say to flip around one of these unit vectors. So it's possible to have a negative j. It would just say travel in the negative y direction. Now that we can visualize these vectors, let's work with them computationally. If we're talking about a vector that starts at P and stops at Q, and we know that the point P has the coordinates 3, 12, 16, and the point Q has the coordinates -4, -3, 2, then we can express the vector PQ in component form or using standard unit vectors. So to create that vector PQ, we need to use that equation that takes the terminal point, subtract the initial point. So for the x components, we will have -4 minus 3. For the y components, -3 minus 12. And for the z components, 2 minus 6. We can simplify that. So our final version of PQ in component form is -7, -15, -4. And if we'd like to write that in the standard unit vector form using the linear combination of standard unit vectors, we just take the component and slap it on one of the unit vectors that corresponds to that component. And that's it. Let's practice using the vector operations that we learned for plane vectors. Let's practice them on vectors in 3 dimensions. So we're given 2 vectors, v and w. And for part A, we're asked to find 3 times v minus 2 times w. So I'm going to go ahead and swap out the v for the components of v. So 3 times the components of v, and then minus 2 times the components of w. And just like the order of operations from algebra, we need to do our scalar multiplication before we can do subtraction. And then we can subtract the corresponding components. Don't forget the minus negative 2, that's a double negative, which will give us a positive. So 3v minus 2w gives us the vector negative 8, 29, 15. Part B asks us to find 5 times the magnitude of w. So let's start first by finding the magnitude of w. To find the magnitude, we square each component, add them up, and then square root. So the magnitude of w looks like root 2. And then if we do 5 times the magnitude of w, then we're really saying 5 times root 2. Part C is asking us to find the magnitude of 5 times w. B and C are similar, but the notation is not the same. Part B says first find the magnitude, then multiply that by 5. Part C says take 5 times w and compute the magnitude. So let's first start by doing 5 times w, which comes out to be the vector 5, negative 5, 0. And then we need to find the magnitude of that. So the magnitude is going to be 5 squared plus negative 5 squared plus 0 squared square rooted. So we've got 25 plus 25 plus 0, or we have root 50. And if we can simplify this radical, then I say we should. 50 is the same thing as 5 times 5 times 2, or 25 times 2. So we can simplify root 50 to be 5 root 2. And if we pay attention to the last problem we just did, we get the same answer. So this is kind of nice. Even though we did these in different orders, we're still getting the same result at the end. Part D, a unit vector that's in the direction of v. So remember that unit vectors are exactly 1 unit long. If I want it to be in the direction of v, then I'm going to take v and divide it by the magnitude of v. So I need the magnitude of v, which is the sum of the squares of each component. So I have negative 2 squared plus 9 squared plus 5 squared, all square rooted, and we can simplify that. We found the magnitude of v to be the square root of 110. So the unit vector that we're looking for would then be negative 2 over root 110, 9 over root 110, and then 5 over root 110. That is a unit vector that is pointing in the same direction as the vector v. We're going to step it up just a little bit. We're working again with a given vector v, a given vector w. We're asked to find a unit vector that points in the direction 5v plus 3w. So the first thing we need to do is find what 5v plus 3w is, and then we can find the unit vector. So starting with 5 times v plus 3 times w, multiply those out, add the corresponding components, and simplify. That is the vector 5v plus 3w. We need a unit vector in this direction. So we'll find the magnitude of that vector. And that comes out to be the square root of 62. Now that we have that magnitude, we can create the unit vector, which takes the vector 5v plus 3w and divides it by the magnitude of that vector that we just found. So the result would be 1, negative 5, 6 divided by root 62. Or we could write that out as 1 over root 62, negative 5 over root 62, and 6 over root 62.